Two of my favorite technologies are mass spectrometry and machine learning. Mass spectrometry gives us lots and lots of biochemical data, and machine learning lets us take data and convert it into complex conclusions. The problem is that raw mass spectrometry data, the way it comes out of the machine, is not ready to connect to machine learning. There are some distinct problems. I have some ideas that will show you how to deal with this. Stay tuned. There are four key ideas when we're trying to connect mass spectrometry to machine learning. Number one, the shape of the training matrix. That is the number of features relative to the number of examples. Number two is how mass spectrometry features can grow and the things we need to keep track of to manage that growth. Number three, we've still got too many features. How do we prune them down? So we're going to prune the feature set. And number four, because the feature set is still so large relative to the number of examples, how do we reduce the strength of the learning algorithm? Let's look at the training matrix. The training matrix has columns for every feature. They're called features in machine learning. And all of our other things, when we talk about mass spectrometry, we call them data points. Same thing, they just represent unique molecules. So we have the number of features across in the columns and the number of examples in the rows, and for every example we have an outcome. This is the decision we would like to make. Now inside the body of the matrix there are the values. So in mass spectrometry the features are the unique molecules, and these are characterized by mass over charge and retention time. The examples are the individual mass spec runs, all with the same preparation. So we have an example from every mass spec run and features each of the unique molecules that were detected. The values inside are the abundance. Now on many mass spec, this is actually the count of the number of molecules detected. On others, it's a value related to that, but not necessarily exactly that. So this is how much of each particular molecule. That's what goes into the value part of the matrix. And then the outcomes, as we've talked about in other videos, we'll continue to talk about, we're doing A-B comparison. We're comparing two sets of examples because that's going to help us focus on our particular biochemical problem. So for every example, we're going to give it an outcome from one of the two possibilities that we've identified for our problem. To understand the shape of the training matrix, let's begin with an example from Google. So this is not any particular Google example, but this is kind of the idea you'll understand. So for features, Google considers 20,000 approximately commonly used words. Those are all the things that they know about documents they're looking at. But for number of examples, they get 14 billion document hits a day. So that's a huge number of examples. Machine learning loves this. The huge number of examples offsets the fact that there are a large number of features. Let's look at mass spectrometry. Mass spectrometry, for any example, we're going to get between 500,000 and 2 million data points or features, depending on the resolution we decide to work at. What we're going to get for examples is frequently 40, 100, sometimes for a really big study we'll get 1,000. But compared to the number of our features, that's a problem. The training matrix is the wrong shape. Instead of being tall and narrow, it's wide in the number of features and short. And machine learning hates training matrices that look like this. Let's look at the nature of the features that we get in mass spectrometry. Now, we need a short definition here. In machine learning, a feature is a particular data value that we're going to consider. In mass spectrometry, a feature is actually a distribution of a molecule, particularly over retention time. They're two different things. So when we're in our mass spectrometry world, we're going to call these data points. And when we're in our machine learning world, which is where we are today, we're going to call them features. So each feature or data point is a rectangle in mass charge. That's what's being measured by the mass spectrometer. And retention time. This is controlled by the chromatography. The values are the sum of all the abundances that occurred in each m over z RT rectangle. Understanding that, now the resolution is how wide is that m over z and how wide in seconds is RT. M over z is measured in Daltons, roughly the mass of a proton. So we'll frequently start out with an m over z of 0.2 Daltons. This is relatively low resolution actually. And we'll use an RT, one of my favorites is 40 seconds in RT. If we divide either one of these resolutions in half, so we go from a 0.2 Daltons to 0.1 Daltons, it's going to double the number of features we have. And if we go from 40 seconds to 20 seconds in RT, it's going to double the number of features we have. So one of the things is going at a lower resolution allows it to be more precise, but it blows up the number of features we have. That's a problem. Now there's another source of growth, and that is the number of examples. If we go from 10 examples to 20 examples, we increase the number of features by about 9%. And if we go from 30 examples to 40 examples, we'll increase the number of features by about 3%. Now one of the things we're going to look at later is that these additional features we keep adding as we add examples are frequently not helpful. So we can go after those and eliminate those, keep our features. Because remember, we got to keep the features down to be able to work with the machine learning. As we're working our way through these ideas, you're going to find a number of things that you're just not going to remember from the video. So if you go down in the description, what you'll find is you'll find a reference to a white paper that outlines these same algorithms. It'll give you more detail, give you a little more substance to program from. So we invite you to do that. As you do that, we've got more to tell you about. In the description below, you're going to find links to things about decision values, links to things about why we do the A/B testing. See the other videos, like, subscribe, set yourself up to notify. We're going to give more videos that are going to fill out more detail on the things that we're covering here. Let's talk about how to prune down our feature set. So the first thing we can do is eliminate irrelevant features. Irrelevant features are features that are not going to really contribute to the decision. Now remember, our fundamental idea is we're doing an A/B comparison, and what we want is we want features that are going to contribute to that comparison. And if they don't, let's get rid of them. Let's get rid of them quickly. The first thing we can do is we're going to alternate adding examples to our set. So we're first going to add an A, and then we're going to add a B, and then we're going to add an A, and then we're going to add a B. After we've done about 10 examples like this, if there are features that are missing that are going to appear later, those features will appear as 0. So what we've got, if we did 10 examples, is we've got 5 A's that are 0 and 5 B's that are 0, and this is confusion. This is a feature that already is demonstrating not to do a very good job of separating A and B. If we're going to get good separation from this initial damaging confusion of 10 zeros, we're going to need 100 or more unconfused examples. That's not very likely. If we got 10 zeros right up front, we're likely to get a lot more zeros. So what we can recognize on this is after we've got 10 to 20 examples, we're not going to get more new features that are going to contribute to our decision. We're going to get more data that's going to help us be more careful with the features we have, but the additional features that we might discover, new spurious molecules that appear, they're not going to be helpful. So we can just forget them. And that's our first step of how to keep the number of features down. Now, if we're keeping the number of features down, one of the things we have to recognize is, are we using stratified sampling? Which in many cases we need to. So we might be stratifying on age, gender, geography, income level. We want to do this stratification because we want to make sure we've got representative data. For all the strata that you've used, for whatever your experiment is, try to get 10 or more examples for each of those strata. Now, there's a lot of overlap, so that doesn't mean if you've got 5 stratas, you've got 50 examples, because each example fits in multiple strata. But you need to consider that. When you got stratified sampling, which is a good idea, you need to consider to make sure you get enough examples so you've accounted for decisions in each of the strata. The next thing we can do is we can eliminate underrepresented features. If we've got our feature set and each one of them consumes less than 10% of the features in each strata, it's unlikely they're actually going to contribute. We can take a pass through. As we've added examples, we've counted how many times each feature appeared, and if it didn't appear very much, get rid of it. We want to make sure we cover our strata, but we want to get rid of everything that isn't going to apply. Now, if you remember from other videos, everything is about an A-B comparison, because an A-B comparison is going to allow us to focus on the molecules that are different. If you haven't seen any of those videos, please look down at the description, because down in the description you'll find references to those videos. You really want to know about asking the right question, and we really want to know about how to compute a decision value. Those two things are going to be essential. Decision values are going to be the key to how we're going to prune down the number of features. For every feature, what we're going to do is we're going to compute a measure of how well does that feature separate A from B. If that decision value measure is less than 1, that means there's a little bit confusion between A and B. They're not completely separate. We may still be able to get value out of them, and machine learning is good at doing that. If it's above 1, then they're separate. They don't overlap with each other. We can divide right here and get a good clean decision, A from B. Higher than 1, it starts to stretch out, and we love these because they've got a nice big gap. A nice big gap that makes it easy for us to recognize when we have A and when we have B. Go back and check the videos on how to compute a decision value. Then what we're going to do is we're going to sort all of our features based on their decision value and look at the top N. So you can see here in the graph over on the right, there's a relatively small number of features here that have really strong decision values. We like those. Now initially what we're going to do is we might keep the top 5,000. We don't want to use 5,000 in our machine learning, but having 5,000 means we've kept almost anything that might have any information about A versus B. We will prune that down later, particularly as we increase our resolution and try to focus on the molecules we care about. The big thing we do to prune down the number of features is decision values. Our last step is the strength of the learning algorithm. What we want is we want a weak algorithm. That is, it's not capable of computing a very large or very complex decision. Because a very complex decision, when applied to a relatively small number of examples, we'll just memorize the examples, and we don't want to do that. We want something that'll generalize. First possibility is a simple vote. We take the top, let's say, 10 features, and we let them all vote on what they think the decision should be. Now, even if the top 10 features have decision values greater than 1, we still might want to vote just to be a little bit more robust in the decision. We've consulted multiple molecules, not just one, in making our decision. Voting, it's simple, it's direct, not very complicated in the things that it can learn, but it will not overfit very often when we've got a small number of examples. Algorithm number 2 is a linear algorithm. A linear algorithm, we demonstrated here, we've got triangles and circles, and they can be separated by the equation of a line in a two-dimensional space. Now, the linear algorithm is not restricted to two-dimensional space. It can be n-dimensional, but this is easy to draw. It also has the attribute that it doesn't overlearn. It's not a very strong learning algorithm. And also, it's very easy to figure out which features were important. So if you have n features and only 3 of them actually make a difference, it's really easy to pick that out of the equation. So it's a very valuable algorithm in that regard. Now here's a second example where we can't draw a straight line between the circles and the triangles. So basically we need a curved line. A standard linear algorithm will not learn this. There are other things that we can do, but again, if we increase the strength of the algorithm, we run the risk of overlearning what our data has to tell us. Algorithm 3 is the decision bush. This is a constrained decision tree. So a decision tree is a long-standing algorithm known in computer science and machine learning. By itself, it's too strong. It will learn basically anything, and we've got too few examples to really grasp what's important. So what we're going to do is we're going to constrain this tree. It's a simple thing. It's just when we reach a certain node, that has less than 10 or 20 examples, we're not going to continue, even though it hasn't completely decided A versus B. What this is going to do is going to keep the tree from getting very deep. Hence, it's a bush. It will learn more complex things than simple linear or voting, but it will give really good identity of what the molecules were that we made their choices over, and it's relatively efficient. In addition, there are algorithms like neural network deep learning, support vector machines, Gaussian mixtures, bagging, boosting, lots and lots and lots of things that we can do. These are all too powerful. They will learn too much of the example and not come up to the general conclusion that we're interested in. So we're going to skip these algorithms. Now, if it happens that you have the money to get 100,000 patient samples, then you've got lots of examples, and then you can go into a more sophisticated learning algorithm. But with the 40 to 100 to 1,000 range that we're working with these days, we need to stay with these weaker decision algorithms. In summary, we first covered the shape of the training matrix. What machine learning likes is it likes a few features and a lot of examples. And what we've got is a lot of features and a very few examples, so we've got to deal with this problem. Then what we did is we looked at what is it causes a growth in features when we're dealing with mass spectrometry. And one of the biggest things is increased resolution. When we reduce the size of the resolution we're looking at in M over Z, or if we reduce the number of seconds we're looking at in retention time, it's going to correspondingly increase the number of features. As we add examples, additional examples are possibly going to have features in them that weren't in the previous examples. This can increase the total number of features. However, it reaches a point where it's just not useful, so make sure you check on that. Third point, we're going to prune the feature set. The number one way you use for pruning the feature set is decision values. We calculate a decision value for every feature or data point, depending on which terminology you're using. And then we take the biggest decision values, the ones that tell us the most about how to separate A from B, and those are the ones we use and pass on to our learning algorithm. Those are also the ones we pass on for interesting biochemistry to consider, because remember, each one of these features corresponds to an individual molecule or a small set of molecules depending on the resolution we're using. Last thing, we use weak learning algorithms. These are algorithms that do not learn really strong, complicated decisions. They are relatively simple decisions because we don't want to overwhelm the knowledge we actually have in our relatively few examples. Thank you for watching. See you next time.